Oh,
'So welcome to Kinematics and Dynamics. Some of you have familiar faces, and then some of you are familiar names where I graded your stuff but never really saw you from statics. I also taught statics. I'm teaching it again this semester and it's also at 2. So if I for some reason start wrapping up at 2:50, just remind me that this is a Tuesday, Thursday class. Maybe not remind me. The like really long classes are so long, they're so hard to pay attention to. I will ask that everyone wear your mask over your mouth and your nose. I have random health issues that I like to have everyone keep your mask on. That would be great. Also with the really long lectures and COVID and just other sicknesses, I am recording all of the lectures. I have them live so you can watch them either with this link here or over on the Zoom tab. And I'm going to post the recorded lectures. So come listen to lecture, watch it online. You can also go back and see the recording. So if you start to zone out for the last 15 minutes, just let yourself zone out, because sometimes forcing yourself to can be really annoying. Also with these really long classes, I'm okay if you have to get up and walk around in the middle of it. That's really like not common, I guess. But I did that a lot under undergrad. My professors didn't like it, but it helped me. So if you need to like stand up and walk out, like I'm okay with that. So they're really long lectures and the material is quite dense. So you're not really going to get a break in lecture necessarily. Congratulations also for passing statics and getting through. The homework for this class is not going to be nearly as dense, thankfully for you, because it is a nightmare. I control this class completely, so that's nice. I'm also not doing Wiley Plus homework. We're going to be turning your homework in still online. You'll take a picture of your PDFs and submit it online. It's just easier to keep track of everything, especially when there's late assignments and such. And in that way, it would essentially be your process document. And I'm not going to have as many homework problems. So that means the homework that you do submit, I want it to be really high quality. So the problem statement's really well written out. The free body diagrams, really well drawn out. In this class, we're going to have motion diagrams too. So everything being defined. Your equations be written out in complete variable form before you put in the values. Just have a really, really nice template for your homework. And I might put up some example problems. And then I do have on here at the end of the syllabus, some instructions on like how to turn in homework. And technically you had this in statics, but I'm going to go over it again when we get closer to the time where we're turning in homework. I haven't posted the homework yet. The first homework set is 5 questions long. And then later they'll get shorter and shorter as the problems get more dense and we start getting more focused. For the homework. So this is the chapter and the sections. I realize the labels aren't here. So for your textbook, which you can find through the bookstore, I advise you to buy it, although I'm going to be writing my own homework questions. But it's going to be helpful in reference. Also in the homework, I'm going to have a list of self-study questions that you'll be required to know. So that's essentially working as many problems as you think that you need in order to be successful on the exam, and you'll be required to know all of that material on the exam. And those will be from the current textbook. I think it's the 9th edition is the one that we're on now, and you can find that through the textbook. And these chapters and sections follow along with that. So today we are on rectilinear and plane curvilinear motion. So we're jumping right into it in a little bit. You'll see that each exam has about 2 homeworks, and then the final has 1 homework's worth of new material, and it is cumulative. Before every exam, and really at the end of each chapter, there's going to be a quiz. And this quiz is not going to be just asking like work a problem with like the acceleration of this, acceleration of that, and solve for t. It's going to be conceptual. Some of the answers will be short answer. So you'll be explaining why there can still be acceleration when the speed is constant. And I even sometimes will say, do not put equations down, because especially when we start getting lots of equations where there's tons of substitutions, we rely on the equations a lot, which is exactly what we're teaching you to do. But I don't want you to forget everything that those equations mean. So the quizzes are going to be much more conceptual. If you listen and lecture and understand the ideas of what I'm talking about, you should have enough of what you need to know for the quiz, because they're more conceptual rather than working actual problems. For the exams, I am going to allow you to have a sheet for equations. On that equation sheet, you cannot have problems worked out. And even if you did, it wouldn't necessarily be helpful because the problems will be different and it takes a lot of time to convert, you know? But just equations. And if we get to the exam and there's an equation that you did not include on your sheet and you feel like would be helpful, if you ask me for it, I'll give it to you. If you know to ask for an equation, you were more than certainly happy to have it. Because in real life, we would be able to Google that. So as long as you know the words and what to ask for, I am happy to give you what you need. Those quizzes are right before all of the homeworks are due. And then final exam, it's on Friday at 4 o'clock, our final. So on the plus side, you'll have a lot of time to study. On the negative side, we're gonna be here till the very end. And I have to grade on Saturday. Not a fan of grading on Saturday, especially in the spring when everything's almost done. Not great. So unfortunately, we have that. Any questions on the syllabus? Topics? Okay. And if you think of any later, you can always email me. My email is here. You can always email me there. I don't have an office. So office hours, I'm still gonna try and figure out. They're always by appointment. So if you need to talk about anything, especially accommodations or grades, anything that needs to be private, let me know. I can schedule us a conference room and we'll meet there. As the semester goes on, more and more of you will have the same kind of problems. So I'm considering having group study sessions where I say, for this study session, this is what we're going to study. It's essentially office hours because everyone is coming to ask questions, but we'll all be looking at the same topics. And that way there can be more time for me to go around. And here's the text here. And it's the 9th edition that we're using this time. There is going to be a final project. And this final project is going to essentially be a complex problem that I would like to put on the final, but we don't have enough time to put on the final. So this will be due before finals week. And in doing this project, you'll be studying for finals, essentially. You can think of it as an extreme homework problem. But with this final project, I'll have you type up rather than just write on your engineering paper some ideas on the project. And I'll give more information about this as we go on. But just know that not all of your grade is going to be coming from exams. I know in statics, a lot of your grade comes from exams, so it's a lot of pressure just on a few days. So in this class, we're having final project, homework and quizzes, 15%, final exam 30, and then exams 1 and 2 are 20% each. And we're doing a prerequisite quiz next week. And then all of the other things that are pretty standard. And if you think of any questions later, just let me know. Okay, I think that was it for here. Now we're getting into the material. So in statics, you looked at some of the forces a lot, and you became a master of summing forces in 1 semester. And every single time acceleration was equal to 0. For this course, however, acceleration is no longer equal to 0, and we really care about this side of the equation a lot. The course is going to be broken down into a few different parts. So this is kinetics when you are just looking at acceleration. If you look at acceleration and forces, sorry, this is kinematics. Kinematics is when you're just looking at acceleration. Kinetics is when you are looking at forces and acceleration. And what we did before with statics is we were just looking at forces. And you might be taking it now or later, but mechanics of materials is looking at the internal forces. So we're not doing this. We are doing statics only in that we are doing kinetics. So you'll have to use all of your skills from statics, but it is not exclusive to statics. Because we haven't done acceleration, we've only done the forces. The first part of the class, or like a third, I think, we'll just be looking at acceleration and learning about acceleration. During that time, don't forget everything that you learned during statics, because later on we're going to combine them together. When looking at acceleration, there's a few different kinds of accelerations. For a velocity vector, you have the magnitude of the velocity times the unit vector. And that unit vector can be composed of the direction vector over the magnitude of that vector, or it can be composed of cosine and sine using some kind of theta. And with this, we can look at the magnitude with that unit vector spread out. If you like to think about this as cosine theta, sine theta, that's a good place to start. But we'll be quickly leaving that because we're going to be taking the time derivative of the unit vector. And it's not always cosine and sine, and as soon as you take a derivative, it changes anyway. So that's what we're familiar with thinking about with these unit vectors, but that's not the only thing we'll think about with the unit vectors. So the three kinds of acceleration coordinate systems. The first is a rectilinear, which is the topic of today's lecture. And with this, we have our magnitude and unit vector, and we don't care at all about the unit vector. All that we care about is this magnitude. So it doesn't matter which direction the velocity is going in, because we're just looking at speed. And you'll often see questions like this if you were to like Google like kinematics or kinetics. There's often talk about you can have a change in speed and also have an acceleration. Our change in speed here with the magnitude has nothing to do with the unit vector. So we'll be looking at that first. The second part of acceleration is rectangular coordinate system. And with this rectangular coordinate system, this is what you became most familiar with. This is the X and the Y hat, where you have the magnitude in with each of the individual parts. And you can even break it up even more to have your V of X component, V of Y. A lot of times we saw that as Fx, Fy. And here we're looking at acceleration in one direction and acceleration perpendicular to that direction. Very much organized based on the dimensions of your system. So if you're looking at a road, one dimension is along the surface of the road. So even if your car hits a bump and goes up in the air, you're just still looking at the speed of the car along that x-axis. The third, we spent a couple minutes of this in statics looking at a tangential coordinate system. And without acceleration, it's hard to grasp how nice the tangential coordinate system is and how simple it can make some problems. Because with this coordinate system, we are breaking up the magnitude and the direction. So we derive the velocity as a magnitude with respect to time, individual of the unit vector as we derive it with respect to time. Whereas for the coordinate system, the rectangular coordinate system, we're deriving the x and y components. So theta is in both Vx and Vy, whereas theta is here and the magnitude here. It simplifies some of your math if you're working it by hand, because the unknowns are a bit more separated. That's where we'll be going for this first portion of the lectures, and then we'll get into some relative velocity and acceleration. Any questions so far? I know this is pretty abstract and you probably don't quite get where I'm going yet. Don't worry, you'll know more about this than you'll ever have wanted to. So rectilinear and tangential go together well because the magnitude, they're treated the same. But rectilinear and rectangular go together well because you can treat this as one speed and this as another and use time and theta to connect the two. So today we're going to start in rectilinear and maybe make it a little bit into rectangular. We'll see how far that we make it. So rectilinear is essentially a straight line, but we know that if we were to travel kind of along a path and you were to calculate the distance from point A to B, calculating the distance not in rectangular coordinate system, you could use the path that is traveled as a tape measure and measure the distance that was walked or driven or rolled. And in this way, that is how we are measuring motion, is by the pure distance traveled by the object. This isn't a straight line though, but it can be treated as a straight line as long as you keep the measurements the same all along the way. So it doesn't have to be in a straight line, but we treat it as if it were in a straight line, which is why it works out to be the x and y in rectangular coordinate systems pretty well. It's because we can treat it as a straight line. From physics, you'll probably remember the equations for velocity and for acceleration. Sometimes I write the d dt on the outside where it kind of multiplies in, and sometimes I'll write it already multiplied in. It doesn't matter, except that you recognize this as something that can come out of it, and that if you had an equation for s, say t squared plus 3, you can plug this equation into s here. So recognize it as the variable, and then d dt being that derivative and integration depending on which way you want to take it. And we'll work an example where we have s as a function of t later. So we have our nice velocities. You probably recognize this, maybe even from high school physics, but certainly from your physics 1 class. And we can take these and make all kinds of equations and do all kinds of substitutions. If we were to take the acceleration, which is dv dt, and multiply it by ds over ds, we can move these around kind of back and forth so that we have a dv over ds. So that's moving this to the left, and we move the dt to the right, ds dt. And this is also velocity. We get another velocity here. Acceleration is equal to the velocity times dv ds. These equations are of great importance. Projectile motion equations are all derived from this concept here. And for homework 1, I actually have you derive the equations for projectile motion. You can use notes and use resources. I don't care how you find it, but I just want to know that you have written it down yourself and kind of understand the substitution to some extent. I won't be asking you to derive problems like that on the exam, but in homework, it's helpful to know where these equations come from. Okay, so if we shift them around, we have A ds equal V dV, A dt equals dV, and V dt equals ds. 3 equations, 3 unknowns. If you had me in statics, I like to count the equations and unknowns a lot. It gives you some information about what you're able to solve and can even give you some input on what you're missing. So if you know that there are 3 unknowns that you're solving for and you can only think of 2 equations, you know that you're missing 1 equation. If you have 4 equations when you probably should only have 3, you know that there's an extra constraint in the problem statement, or that you may have done some substitution and made 2 equations that are the same. They might look different, but functionally they're the same. So here we have our 3 equations. To do some more integration and substitutions, let's first take V ds dt. And when we moved it to the other side, which I believe we already did, and integrating, velocity changes with respect to time. So that will be V final minus V initial times T. No. For this one, we're actually going to assume that this is an average. And sometimes we will assume average velocities and sometimes we won't. And for this equation that we're going to derive right now, we're going to assume that this is an average velocity. So velocity over time remains constant. So here we're looking at a constant velocity. So velocity T final minus T naught. And in all these problems, we're going to assume that T naught is equal to 0. So we can actually just leave off the T naught. I'm not going to for right now. And then for our position, our final position minus our initial position. And if you were to solve for velocity, you will get this equation that you might recognize for average velocity. Because we're assuming that the velocity at the initial is the same as the velocity at the end. But in most cases, we're going to have accelerations. That's not overly helpful, but for average velocity, that equation does work out well. Looking back at acceleration times dt equals dv. Integrating this, we will get at constant velocity. This class, we're, other than one example problem that we're about to work, we're going to be looking at constant acceleration. That is a class for the future if you are interested. So constant acceleration, AT, remembering that T naught is equal to 0, and we'll have T final just equal T. And then for our velocity, final minus initial, notice that this velocity does change with respect to time. Then we look at our next equation, V dV A ds. Integrating here, V squared final minus V naught squared equals A S final minus S naught. Shifting these around, so we solve for v of f, multiply by 2, and then move v naught squared to the other side. Hopefully these are starting to become a little bit more familiar as we're working through them. And now we get to the fun part, because we are going to use v ds dt again, where we can bring dt ds. However, this time we do not want an average velocity. We want a velocity that changes with respect to time. The way that we used it before, we didn't have any information about acceleration. So we just assumed that velocity was constant. Here, we are not going to assume that. In order to assume or to solve for this, we have to do some substitutions by taking this equation here, solving for v final, which will equal v naught plus at. We are going to say that we're looking at the final position. So if you say I'm looking at a projectile motion as it goes into space, I'm going to analyze it as it gets 200 feet above the ground. We're looking at the velocity at 200 feet above the ground. Therefore, we can say that this velocity here is the final velocity. And that's why this substitution works. You could also look at the initial velocity. You would just solve for the initial velocity and move everything else around. But I don't really know when that would be helpful. Maybe it is helpful. I've never seen it done before. So usually you just solve for the final velocity. And that leaves v naught plus at times dt times ds. And now we have a nice equation that brings in velocity with acceleration and with time and with displacement. V naught t plus 1/2 at squared equals s final minus s initial. Shifting these around where you can solve for s final. So really we're looking for that 200 feet above the ground here. S final is equal to s naught plus v naught t plus 1/2 at squared. These are equations that would be helpful to have on your equation sheet. If for some reason you come in and realize that you have not included them on your equation sheet, definitely feel free to ask. I'll be happy to give them to you. But I know it can be nice to have the equations written in your own hand and you've already looked at them before coming in and whatnot. So these are the three equations that came from those three equations that we set up before. Projectile motion, rectilinear motion. These will be what you want to use. Notice, however, that these are all in terms of s. So s isn't necessarily given a direction, it's the distance traveled. But you can easily say that this distance traveled is along the x-axis. Therefore, my value of s equals x. And you can put in x components for all of these values. Likewise, you can put y component for all of these values. I'm not going to work through the derivation again for rectilinear motion. This is what you can do on your homework, is you'll take the derivation that I just did. You can even do it step by step, how I have it laid out. X, y, instead of having s, you have x. Instead of having y, you have, or sorry, instead of having s, you have y. Be careful though, because now the velocity isn't just blank. Instead of just velocity, you'll have v of x if you're in the x component, And instead of just velocity, you'll have v of y. So be sure to identify both ways, x and y components when you're doing that derivation. I'm incredibly lazy and I like to leave off like identifiers whenever I can, because it just takes extra time to write and my handwriting's pretty bad. However, in this class, all of these subscripts that define your variable will be required. If on the exam you give me an equation that has a velocity just like that, instead of a velocity x or a velocity defined in some kind of way, I will count off points because you dropped that subscript, even if the number that you put in that variable was correct. So you knew what was going on, but you have to communicate to me that you know what's going on. And it is incredibly hard, especially later in this class when we get all kinds of variables of velocity and acceleration flying around, doing relativity, not knowing what the variables are, or just holding them all in your head. The more times you hold things into your head, information about your variables, the harder it is to process new information. So write down what all the variables mean as much as you can. And this is especially true for homework because you do have more time to go back and check your subscripts. If you have lines and lines of equations on your exam and you have all the subscripts except for one, that's a little bit different because I know you just dropped it. But if you're putting lots of equations down with no subscripts, that's going to be a red flag for me. Any questions on this derivation? Okay. And if you have any later on, just let me know. The curved linear motion, I prefer to actually talk about that when we get into normal and tangential, because normal and tangential is much more connected to rotations. So we're actually going to hop into a rectangular coordinate system now. Because in some ways, we've already been working in rectangular coordinate system. So this is just to say that S is along the x-axis and another S, so let's say S2 is along the y-axis. And why we like to break these down into perpendicular components is because when we're dealing with forces, especially adding vectors together and moving vectors around, you add vectors that are parallel to one another. And if there is a vector that is perpendicular and there's a moment arm, that creates a moment. So it's helpful for us to identify our acceleration and velocity components in the same components that we define our forces in. If you had me for statics, and even your own professor for statics, may have often written down forces in vector form and notated that you're writing it in vector form. And this is all in vector form. We're starting to get in the reason why. It's because you connect everything together in vector form, and it's a lot easier to handle mathematically than dealing in magnitude. Like using the law of cosines and sines is okay. You can add two vectors that way together in statics, but it's not the best way when you're wanting to relate it to acceleration as well. So for the x, v of x equals d of x over dt, a of x equals d vx over dt, and the substitution where we have an equation that only has velocity, acceleration, and position. And you'll need to show me the derivation to get to this point and then to get to the later equations. And to do that, you multiply an equation by dx over dx, just like before when we multiplied by dy or ds over ds. So those are the three along the x-axis. Three unknowns like before. However, now we can multiply it by 2 because we have vy. Ay dvy over dt. And then lastly, ay times dy equals vy times dvy. And for this, you multiply by dy over dy. 3 more unknowns. Now we have a total of 6 unknowns that we can handle, 6 equations, 6 unknowns. Unlike before, there's not overly clear ways that these can be substituted in with one another to solve them. How you would do that is if you had your velocity vector or your acceleration vector, or whatever vector you're looking at, it's connected by the direction. So theta or the unit vector, however it's written down. A lot of times in projectile motion equations, they'll ask you for the angle. So that's going to be theta. Another way they are connected is time. Your stopwatch works the same whether it's in the X or whether it's in the Y. If you're working a problem with rectangular components and you are confused on what to substitute and where, if all else fails, solve for time. Time is a lot easier to solve for because theta is in the X and in the Y. So cosine X or cosine theta, sine theta. So it's X and Y. Time is a little bit easier to solve for by hand. So if you're at all lost, just solve for time. That's a pretty good guess. It's not always the easiest place to start, but you usually have to get there because time is how you connect the X and the Y components with one another. And there's often a double substitution where you have simultaneous equations with theta and time. In those cases, I won't ask that on an exam, or I will provide you theta or something like that to be able to solve for them by hand. But on your homework, you'll have a little bit more time to solve these. So you might have to use some kind of simultaneous calculator. Any questions on how this connects? Okay, let us move on. The equations that you will be solving for, and these are provided in your homework as well. Part of me is trying to get this written down a million times so that you write it down a million times so you can become even more familiar with it. And notice all of the subscripts I have here. Subscripts now have an X component and it is the final velocity. X component and it is the initial velocity. We're going to eventually be getting lots and lots of subscripts to define our variables. And this is just the start. And for y of f equals y naught plus vy times t. I skipped one. And I also want to note that this is at first average velocity. And here we have our third one. X final equals x naught plus v x naught times t plus 1/2 ax t squared. And now we can go on to our y. For our average velocity, y sub f is equal to y naught plus vy times t for average velocity. Y of f equals, I just wrote that, vy sub f equals vy naught plus ay times t. Vyf squared is equal to vy naught squared plus 2 ay times y sub f minus y naught. And the last equation is y sub f equals y naught plus vy naught times t plus 1/2 ay times t squared. So we know that theta and time connect the x and y components with one another, but there's a few other places where projectile motion gives us some tips about the velocity. If you have projectile motion and it is traveling in a curve, at the very, very top is a helpful point, because if you have a velocity going up and then you have a velocity going down, at some point you have a velocity going exactly flat, and that's going to be at the top. It's going to be exactly flat. At this point, our object that is flying in the air will have no vertical velocity because it is exactly flat. So this location is called the apex. At the apex, Vy is equal to 0. That's a really important point, often too, because unless there's some odd constraint, the apex will typically be exactly halfway. Sometimes there might be a distance given that's like a box or something up here, so that won't necessarily be true, but if you're landing just as high as you took off, then that apex will be exactly halfway. Another thing to note about projectile motion is we're typically working in a world where there's gravity. And in this class, we are assuming that drag is equal to 0. Sometimes, occasionally, there might be a rocket where acceleration in the x direction does not equal 0. But for the most part, acceleration in the x direction for projectile motions in this class is equal to 0. And for that reason, the velocity x naught is equal to the velocity x final. Realistically, in life, we know this not to be true because the world isn't in our hypothetical. But thankfully for us, in the math that we're going to have to work out by hand, we are working in a hypothetical world, simplifying these problems. But later on, when you are working with drag, there is a location to put that in these equations. Just for now, we're assuming that it is 0. Gravity does have an acceleration in the y direction, which is 9.81 meters per second squared. Notice that, and we'll get into directions later. So there is acceleration in the y direction. This is acceleration in motion because our object is free to move. We are not thinking about mass at all right now, so don't think about this in terms of weight. Later in the semester, we're going to have equations that have weight due to gravity and the acceleration that your particle is moving at the speed of gravity, or 9.81 meters per second. So be careful to keep them clearly separated in your mind. Here we have an object in free fall with no drag moving at an acceleration that is equal to gravity. And when we get into kinetics, I'm going to talk more about mass and how that's connected with gravity. But for now, this is not the weight due to gravity. This is the speed because of gravity, so free falling. And we're not dealing with any kind of like terminal velocity things. We're just looking at plain acceleration due to gravity. Okay, any questions about all of this theory? We will get into some example problems that we will most likely finish up next time. Okay. So we have an automobile that's moving at a speed of 60 miles per hour. Notice that it says speed. This should immediately tell us that if we have a velocity vector, this is the only information that we were given. And this is also incredibly important when we get to normal and tangential. But for now, speed. We only know information about how fast it's moving. We do not have any information on where it is moving. It could be moving all along the X. It could be moving all along the Y. We don't know, and we don't really care. So if the driver applies brakes and accelerates opposite of motion, also known as deceleration. Which, if I was in charge of the way that people spoke, I would make deceleration not a word, because I can't stand it. It's negative acceleration. One time I had a professor that the entire class, she talked about the rate of change of velocity, never acceleration or deceleration, because she also hated the word deceleration, but it was, I studied biomechanics, and it was like a human motion class. And like if you're running and you slow down, no one would say you negatively accelerated. That's just weird. So she always talk about the rate of change of velocity and acceleration and deceleration. But I know we live in a world where if I said negatively accelerated, I already get enough grief for how nerdy I am. So I just need to stop there. So this is deceleration. In this class, I'll be sure to, whenever I say deceleration, remind you that it actually is negative acceleration. So applies brakes to slow down. Also, you could just say slow down. That's another easy way to define what's going on here. So slowing down here at a constant rate of 10 feet per second squared. Notice that that acceleration I'm just giving in terms of magnitude. I haven't assigned any positive or negative value. I've just put it in magnitude and let this define my direction of it. Because for speed, we don't have a direction of speed. So how can we have a direction of acceleration, which is the argument for saying that negative acceleration is wrong? I don't like it, but there's not a really good alternative. So here I'm putting my acceleration as magnitude and letting the description of the words let me know which direction it is. So we are to find time and distance in order for our automobile to stop. So stopping is V final equals 0. So V naught is equal 60 miles per hour, which if you wanted to convert it, which we will in a second, you'll need to do that. Make sure that all of your units are consistent with one another. And we know that acceleration is constant. So A naught is equal 10 feet per second squares, and A final is equal to 10 feet per second squares. You don't need to write A naught and A final. That's not a requirement, but I like to emphasize that there is acceleration at the initial and acceleration at the final. We can go through and erase that and have it just called A, but know that it is a constant acceleration that goes through the whole time. We have our 3 equations with constant acceleration. That first of the 4 equations that we looked at was average velocity. But now we're going to be looking at constant acceleration to find time and distance. Notice that there's a third unknown that we could find, but we don't need to here. So we're just looking for two unknowns. 60 miles per hour can be converted by 5 to 80 feet per mile times 1 hour over 300 or 3,600 seconds. And V naught will equal 88 feet per second. V final 0, acceleration 10 meters, nope, 10 feet per second squares opposed to motion. So looking at V final equals V naught plus AT, and V final squared equals V naught squared plus 2AS. Remember that we're looking for time and we're looking for the total distance. If all else fails in your calculations and you don't know what to solve for time. That's always a good constraint. It's in most of the equations, so it carries around your constraints fairly well. So in this problem, we have an initial velocity, a final velocity, and an acceleration. Final velocity, initial velocity, acceleration, the only unknown is time. We can take this time and then solve for other values, but when we use the equation that did the substitution ds over ds, we find an equation that does not have time. If you can use this equation instead of having that time, it can be helpful if you mess up the calculation for time in some way. It keeps you from making mistakes. We have a velocity final, V naught, and acceleration. S is now the unknown. So let's plug these values in and solve for time and position. So V final is equal to 0, 88 feet per second plus 10 feet per second squared times t. Solving for t, 8.8 seconds. Velocity final again is 0. The initial 88 feet per second squared plus 2 10 feet per second squared times s. Solving for position at the very end where that final velocity is equal to 0 will give us a distance of 387.2 feet. Now we've done some nice rectilinear motion. The next example problem will be doing the same thing, but in X and in Y. Yes. That's a great point. Yeah, because of opposed to motion. Yeah, if you solve this, you will find out that the time would have been negative, which is not true. So this 10 would be negative here because it's going opposed to the motion. Thank you for that. And 10 here. And if I worked this out on my calculator, I would have come out with negative values. And that is always a big sign that you've done the wrong thing. If you get a negative time or negative distance, technically you can walk backwards, and technically there was time in the past, but we're not measuring backwards in time or in space. So negative values always should be a red flag to you that you've messed up either your calculations or the equations. Any more questions here? So this next problem is projectile motion problem. Where the velocity is going out just to the side. So v of y naught is equal to 0. The unknown in this problem is v of x naught. We don't know what vx naught is, but we're given all the other values. Words in the problem statement will describe the situation, saying that velocity is shot out at horizontal. What is the la da 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 da? So if you read the problem statement, look out for words like it's shot vertically or it's shot horizontally. Any kind of words describing a direction will often simplify your problem and get rid of variables. So here our vy naught is 0 because this problem has a projectile getting shot out horizontally from, it doesn't say, we'll say a cannon. That's always fun. So it's initially shot out horizontally, and it goes to a point B. This vertical is 50 meters, horizontal is 40 meters, and this here is 20 meters. Sometimes there's going to be information in the problem that you don't need. If you think about it, the vertical distance traveled by this projectile motion is 20 meters. This 50 meters doesn't really matter. Often what's difficult in projectile motion problems is there becomes so much information and so many variables that it can be hard to organize your thoughts and get everything together. The algebraic substitution isn't that complicated, but organizing your thoughts in order to put them in the equations can be. So be wary of excessive information that is not needed, whittling down into what you do need. So even though this 50 meters and the 40 meters is given in the problem statement, I'm gonna erase the 50 meters and we'll keep that 40 meters because that's the distance traveled in the x direction. But we don't necessarily need to know how far down this goes. We can just treat it as dots going down this way and move up our 40. This didn't change any of the information that we needed because we have all of the x and all of the y, but it might simplify down visually even to help you focus on what's actually important. So for this problem, we are assuming that x naught is equal to 0 and y naught is equal to 0. So our coordinate system, x and y are here. So our origin is at A. We'll have B with respect to A. The x distance is 40 meters and the y distance is going down 20 meters. Essentially what this problem is a projectile motion problem where you're given the information at the apex. Also, if you want to think about it that way. Because our Vx naught is equal to an unknown value, Vy naught is equal to 0. This often happens at the apex. Remember, we don't have drag or anything, so acceleration in the x direction is equal to 0. We're assuming that our object is free falling. Therefore, it is in the negative y direction. So not only are we going to need to find the value that we're asked to find, we need to find time. It does not ask us to find time. And it doesn't initially seem like we need to find time. But remember, the way that X and Y are connected to one another are with angles, and our theta equals 0. So time is going to be the best variable to connect the X and Y components. Measuring with your stopwatch in the X direction and the Y direction is exactly the same. So in this problem, when all else fails, solve for time as well. Any question on the problem setup? If you're feeling lost in these problems, write out all of your information in some kind of table or graph. That can help a lot. Sometimes I'll write it X and Y on one side, or I might write initial and final conditions on the other. Here I just listed it out vertically, but there's a lot of ways to organize your information. Play around with it with example problems to figure out which way that you like it best for you. So some equations that will be handy are ones that we've already derived. X final equals X naught plus V X naught times T plus 1/2 AX T squared. And we know that our AX is equal to 0. You can write that in and then set it equal to 0, or just erase it from the beginning. I don't really care either one. I will often write it in just so that you remember it's there, but you don't need to. I won't count off if you don't include it. Another equation that might come in handy is F, or Y of F equals Y naught plus the velocity Y naught times T plus 1/2 AY T squared. And in this equation, we cannot set AY equal to 0 because there is gravity. We have the final position, initial position in both X and Y. We know the acceleration in the Y direction. We don't know time. And we also don't know our initial velocity. This is an unknown. There is one other group of variables here that we can set equal to 0. Does anyone see which one that is? Yeah. Yes. Equals to 0. Nice. Nice, nice. So you can read the problem statement and see that horizontal, no velocity in the Y. But if you thought about that initially and then forgot about it and got here, when you're going back and looking through your unknown chart, because you have that written down, it's easy to substitute that in and see that it is equal to 0. So these equations, when we plug in what is 0, are much easier. Because they're like this. Both of them dropped a variable, so they're not too long. And we're setting these equal to 0 as well, simplifying it down even more. Mathematically, to solve these by hand, quite simple. We can solve first for time, and then second for the X naught. If you don't quite see the full picture before you start calculating numbers, that's okay. Because as long as you get there and set the right things down to 0, you probably will find your way, especially if you use the assumption that you might need to get time. So let's do that in these last minutes. So 40. Yeah. Okay. So 40 equals 1/2 9.81 meters per second squared times t squared. You get a plus and minus when you take the square root, but we're looking at this problem and saying that we are not going backwards in time, so it will just be positive. So 2.02 seconds. And the second equation the final is 20 meters equals to Vx naught times t, which we now know to be 2.02. Vx naught equals 19.81 meters per second.
It should be 40 on the
Other way?
left-hand side instead of 20.
Did I mix them up?
The answer's right. You just put 20 equal to Vx naught times 2.02. That should be 40.
This one should be 20, right?
Yeah, and then the extra.
It's the horizontal distance.
I erased it and put 20 back in, didn't I? Oh my goodness. So this is a negative because it's going down. And this is also negative because it's going down. If you had felt like that, you could flip your coordinate system from the beginning, but you don't need to do that. All right, any questions or comments on this? You got a nice deep dive into today. Next class, we're going to get into normal tangential. I'll be posting the homework soon. It's not quite up yet. Be sure to ask me questions. The Zoom link will be up probably this afternoon. If you'd like to just watch it again, you know, for fun. If not, I'll see you guys on Tuesday.